let's use Cramer's rule to solve this system. Now first off, the system needs to be in standard form. We've already got the 11x plus 6y is equal to 8 written in standard form. The second equation needs that 9y on the left, so 2x minus 9y is equal to 5. Yes, this might be a lot quicker using substitution, but let's go with determinants and Cramer's rule. We begin by finding what's called determinant D, which consists of all the coefficients to the left of the equal signs. So I'm going to write it this way here. Notice all the numbers to the left of the equal sign are there. Evaluating this determinant, on one diagonal I have negative 99. The other diagonal would be 12, but I change it to a negative 12, and I add these two together to get negative 111. Now, I always do this first because I need to make sure that D is not equal to 0. If D is equal to 0, I've got a problem, and it's either a no solution or all real numbers type of problem. We've not used the 8 and the 5 yet, and what we're going to do is we're going to find two more determinants, which we will call dx and dy. For dx, we will put the 8 and the 5 in the first column, and for dy, we will put the 8 and the 5 in the second column. It's kind of like we have an x column and a y column anyways. For dx, we've got the first column. We need the second column, which will be the original y coefficients of 6 and negative 9. And for dy, we've got our y column filled in. We need the original coefficients of x, which are 11 and 2. So we will now evaluate each of these determinants. For dx, 8 times negative 9 is negative 72. And multiplying upward, 5 times 6 is 30, but we change it to a negative 30. Add these two together, we get negative 102. Let's look at dy. First diagonal, 11 times 5 is 55. Next diagonal would be 16, but we change it to a negative 16. Add together and get 39. Okay, so far so good. This is just a bunch of cutesy little stuff. Cramer's rule says that the solution to this system is going to be dx over d, comma, dy over d, and if there was a z, dz over d after that. So for us, this will become negative 102 over negative 111, comma, 39 over negative 111. If you reduce these, you get a solution set here of 34 37ths, comma, negative 13 37ths. Now we look at that answer and we go, oh yuck, but quite honestly, we never got the fractions until the very end. Had you solved this by elimination or substitution, you would have found one of these ugly fractions and then kind of moaned and groaned a little bit about having to substitute that in to go find the other variable. This is kind of a nice method when fractions are your answers because you don't see those fractions until the very end of the problem. Okay, we have another problem they want us to solve using Cramer's rule, and the first thing we want to do is put these in a nice, neat standard form. So the first equation, when I bring that 4y to the left, gives us x minus 4y is equal to 5. The second equation becomes 3x. That'll be a minus 12, so I'll move it to the right as a positive 12. Subtract that 12y to the left, we get a minus 12y. Now I notice right off the bat that my first equation, multiply by 3, multiply by 3, multiply, oops, not by 3. It almost looks like the same line, but it turns out they're going to be parallel to each other and there will be no solution. Let's see what happens when we use our determinant method. We go to find matrix or determinant D. We put in the coefficients to the left of the equal sign, 1, 3, negative 4, and negative 12. We multiply down our first diagonal to get negative 12. We multiply up to get negative 12, change that to a positive 12, and we get 0. If we were to use Cramer's rule, we'd end up getting dx over 0, comma, dy over 0, which would be undefined, and that tells us we've got a problem. So we cannot use Cramer's rule, which is fine because we already know what happens in this problem. We know that our two lines are parallel and there will be no solution.